In our last lecture, we had considered the B-spline functions of order 0, 1, and then we considered of order 3, that is to say the cubic B-spline functions. And basically we saw there that how one can use these kind of interpolating functions in various applications, like in image resampling after rotation, or image resampling after magnification or reduction of images, or in various kind of raster changes, where we have to map from one set of rasters to another set of rasters. To do that interpolation and resampling, how we can make use of these. These are what we saw in our last class. Now, there might have been some doubts or some questions related to whatever we were discussing in the last class. Particularly we were talking, you remember, we were talking of the low frequency content and high frequency content of the images, and we also said the terminologies like low pass filtering, high pass filtering of images. So, since we haven't yet gone into the image filters, we are going to do that after a few lectures, or we haven't even got an idea about the frequency domain analysis of images, I think we can spend a brief time to clarify your doubts on these aspects. The first thing is that about the image filters, or about the high frequency or low frequency component of images, I think it is very easy to draw the analogy with one-dimensional signals. Now, let us consider some one-dimensional signals, say a time signal, which is something like this. So, this is the axis of time, and in this axis we have the amplitude of the signal, and if the signal is something like this with respect to time, what we are really having is, we have very sharp transitions, okay, quite sharp and quick transitions are there in this signal, and if we do the Fourier analysis of this signal, we will find that these kind of signals are rich in high frequency components as compared to maybe some kind of signals like this. If we have a signal like this, you can clearly see that this has got very slow variations with respect to time. So, if we compare this signal with this signal, this top one with the bottom one, we can always say that the top signal is richer in high frequency component as compared to this bottom, as compared to the signal which is shown below. Now, very similarly, we can draw its analogy in the spatial domain. In the case of images, what we are really having is not this kind of amplitude variation with respect to time, but amplitude variation with respect to space. And space means we have to consider the x dimension as well as the y dimension of the image. So, for any typical image, okay, we may have the variation like this. Say in the x direction, maybe that we are having some kind of variations like this. This is with respect to, let us say, x direction, and this is the amplitude. And supposing we take this particular interval to be equivalent to 1 pixel space. So, what we are having? We are having alternate dark and bright pixels, right? For this pixel the intensity is low, for this pixel the intensity is high. So, every alternate pixel is changing its intensity level, and the same thing may be there in y, or in y direction the changes may be slightly different, whatever it may be. Now, really speaking, what we have for this kind of signals is, we clearly see that there are sharp transitions in the x direction. Now, if we take yet another signal where we say that that particular signal is bright for several pixels, maybe for 7 or 8 pixels it is at the bright level or high intensity level, and for the next 7 or 8 pixels it is for the low intensity level. If we have a signal like this, clearly this kind of signal has got much lesser frequency component, or rather this is a much lower frequency signal as compared to this one. In the extreme, if an image, okay, contains absolutely uniform and constant brightness region, if we have an image, okay, where let us say we have at all points we have f of xy being the image function equal to some constant k. If we have that, then very clearly that image has got only the DC component, or only the zero frequency component is existing. Likewise, whenever we have a time signal, and if that signal is constant with respect to time, this is the time axis, and let us say that this is some amplitude v, and that constant amplitude v is maintained with respect to time, we call that particular signal is a DC signal. Very similarly, this is a low frequency signal which we got. So, this is about, this is what I qualitatively meant when I talked of high frequency component and low frequency components of images. So, definitely it just suffices to understand at this stage, before we go over to the detailed aspects of image filtering and frequency domain analysis and all that, it just suffices to say that if we have an image where transitions in intensity are quite sharp, okay, we can say that those images are rich in high frequency components, and the images which are relatively, have relatively smoother variations in intensity, we will say that those images are rich in the lower frequency components. Now, just to explain you the terms of high frequency filtering and low frequency filtering, and here also we can draw a very similar analogy with the time domain signals. Now, for a time domain signal, something like this, supposing we have a time domain signal of this nature. This is quite rich in high frequency component, and let us say that we would like to take samples of this particular signal. Now, naturally we can take samples at a rate higher than twice the maximum bandwidth content of the signal. Now, if we try to do that, then obviously we have to keep a very high sampling rate, because as I find clearly from this kind of a signal that it is quite rich in the high frequency component. So, naturally what we need to do is that if we find that such high frequency components are really some unwanted components, or which are not part of the actual data, like say for example, we may be having a sinusoidal signal of this nature, okay, and maybe at some particular points, say at this point or somewhere over here, there are some variations in the intensity level, okay. Rather, there are some transitions in between. Now, these are clearly noise. Some noise has given rise to the waveform like this. So, if we do a low pass filtering of this signal, rather if we allow only the sinusoidal component to get passed through that filter, and if we do not allow the higher frequency components, then very clearly we can get rid of this type of noise signals, okay. So, that means to say by doing a low pass filtering. So, really speaking, in its frequency domain, what we are trying to get is that an ideal low pass filter will have a characteristic of this nature, okay, where this axis we have the frequency and this axis we have the amplitude. So, naturally, it is allowing all the lower frequency components to pass through, and it is not allowing the higher frequency components to go through. Now, this is quite unrealistic filter, quite an unrealistic filter in the sense that we really cannot achieve such a kind of ideal low pass filter in practice. So, in practice, the low pass filter characteristic may be something of this nature. That is to say, in the pass band, this band we call as the pass band, and away from the pass band what we have is a stop band for this. Now, really speaking, the pass band characteristic will not be as uniform as the ideal. There will be some droop here, okay, and even in the stop band where we ideally want an absolute cutoff, okay, there will be some components, okay, which will be passed in the stop band, okay. So, this is a typical non-ideal kind of a filtering, but this is a low pass filter because as we go to the higher and higher frequencies, okay, the higher frequency components are being suppressed more and more by this kind of a filter. Now, in the case of interpolation, what we are doing is something like this. Supposing we have been given the image data at the integer grid points. Supposing these are the integer grid points where we have the image data available with us. Now, what we are doing in order to find the intensity at some point in between, okay, we are considering the effects of the neighborhood pixels, okay, which are at a closer distance, the pixels which are at a closer distance from the point at which we would like to interpolate the image function. We will take its contributions and then we will sum up all the contributions and we will get the interpolated value of that signal. So, really speaking, what we are trying to do is that we are doing some kind of a local averaging. It is not a uniform averaging because it is not that we are taking all these 4 intensity values and then summing up and dividing it by 4. Really speaking, what we are doing is a weighted local addition. It is a weighted local averaging which we are doing. And the moment we are doing an averaging, there is always a smoothing effect. That is to say, we are taking 3-4 pixels together and then we are deciding on a value for the pixel under consideration. So, if there are some sharp transitions in the intensity levels of the neighborhood pixels, whenever we are trying to interpolate the value within some point, okay, the effects of such sharp transitions are really, somewhat smoothened out. So, that means to say, by doing a kind of local averaging or to say the weighted local averaging, what we are doing, we are eliminating or reducing the effects of the higher frequency data components. So, that is why I said in the last class that while doing the interpolation, we are also doing a kind of low pass filtering. Now, the analogy is very clear, like the way for the time domain low pass filters, we have the frequency on this axis and amplitude on this axis, okay. Very similarly, for the low pass filtering of images, we are going to have this kind of amplitude versus frequency characteristics. But in that case, in the case of images, what we mean by frequency is the spatial frequency. That means to say that how the image data is varying in space, the frequency of that. So, we are going to have the spatial frequency components in x direction and in the y direction. And whenever we are talking of a low pass filtering in images, really speaking, we are talking of low pass filter in the spatial frequency domain. Is that clear to all of you? Or any doubts still on the terms which we have talked about in the last class? So, in the last class, you remember we had said one thing, I think in connection with the magnification or reduction of images. I think in magnification of images only we had said that there are two methods. One is that we can magnify by pixel replication. Okay, by replicating the number of pixels we can magnify the image, or the other the thing which we can do is that we can do interpolation on the image data and then we can resample and get an enlarged image. These two things are possible, and we had said that the difference is that in the case of pixel replication we are mostly retaining the high frequency components, okay, whereas in the case of the interpolation the image is relatively smoothed out. Now, wherever we have some unwanted data, unwanted high frequency noise, or if the image is quite rich in the lower frequency component, in that case we can do interpolation and then resampling. Whereas if the data itself is such that we have high frequency components which are present, okay, then rather than doing interpolation, because interpolation is going to kill such high frequency components, so instead of doing such kind of pixel replication we will be doing the local averaging and or rather we will be doing interpolation, okay, which will do the effects of local averaging. Is that clear? Now, let me also give you the physical interpretation of the interpolating function which we had got. Again, if I give you the analogy of a one-dimensional signal, you can extend this very easily to two-dimensional signals. Let us say that we have a data like this. This is amplitude, this is time, and what we have in this case is a discrete data. Our input data is a discrete set of points. So, we have taken the samples at these instants. Whatever I am marking now, at these instants we are taking the samples. So, the samples will look something like this possibly. And our objective now is to find out the intensity value at some point in between. Okay. So, that means to say from this set of discrete points, okay, we are going to reconstruct a continuous waveform, or rather we are going to approximate a continuous waveform, because we have already lost the original continuous waveform because we have taken the samples, we have lost the original data, but because we have got sufficient number of samples present, okay, we can at least do a good approximation to find out the intensity value within these points. And there we said that in order to do that, we will make use of interpolation. Now, one such interpolation function I said was the nearest neighbor, which is very clearly understood. Okay, I think none of you will be having some doubts, because it is very clear that it is like a sample and hold function, or in the case of nearest neighbor, like as long as I am within the distance of minus half a pixel or plus half a pixel from this point, okay, its interpolated data will be same as this sample. Whereas, let us now consider the effects of the first order spline or higher order spline. Let us consider the spline functions of this nature. You remember, this is the spline function of order, B spline function of order 1. Okay, this is B1 which we had got. Okay, this is at a distance of 1 pixel, this is at a distance of 1 pixel. Now, whenever we are applying this kind of a spline function for interpolation on this image, okay, what we are doing is a convolution of this signal, okay, which we have now as a set of discrete samples. We are going to consider its convolution with this kind of a interpolating function. So really speaking, what we will be doing is that we will take this function and we will sweep it over this space, okay. And while we are doing the sweep, let us see what happens to the signal. So on this axis, let us say that we are considering data. So here we have the original samples something like this, or let us draw it on this only, on this waveform, so that it is easy for you to understand. So as a result of sweeping this kind of a function over all this set of samples, wherever we have the samples effects are being felt within this plus minus 1 pixel distance. Let us say if we have an image, okay, let us say we have an image where we have a unit impulse, just a single impulse, okay, and at all other points let us assume that the intensity value is 0, a one dimensional profile we are taking. Now for such a kind of waveform, if we sweep this function, okay, in this manner, then we are going to have the reconstructed image function like this. That means to say that within a zone of plus 1 and minus 1 from this pixel, we are going to find its effect. The effect of this pixel is gradually dying down as we move away from this pixel, okay, and away from a distance of plus 1 and minus 1, we find that the function value is 0. So for a unit impulse, the interpolated function will be just like this, but in this case the interpolated function will be nothing but the summation of all these functions which we have got. So that means to say that if we are trying to get the value at this point, let us say at this particular point, if we are going to get the value of the interpolated function, it will be the sum of this interpolating function and also the sum of this interpolating function, sum of these two. So possibly somewhere here the interpolating point will be formed. So maybe that after interpolation and after summing up, we will get the points something like this. So if we are trying to reconstruct the original waveform, or rather the continuous waveform, maybe this is the nature of the function which we will get, means this top red which I am drawing, which is nothing but the summation of all these individual interpolation effects, okay. Is that clear? So this is the physical interpretation of our interpolating function. So really speaking, what we have to do, we have to convolve the original function with this kind of interpolating function, and then what we are get is the combined effect of this. Now in the case of linear interpolation, the effect is only between pixel distance of plus 1 and minus 1, whereas in the case of cubic convolution, we are going to get its effect within plus 2 and minus 2, okay. Any doubts? Any clarifications? Okay. Now let me go over to the topic of discussion for today, which is on the perspective transformations. Now in the last class, if we remember, the last 5 or 10 minutes I had spent on defining the basic geometric transformations in the 3D space. So if you remember, we had expressed all the basic operations like translation, rotation about any axis, translation, rotation and scaling we had expressed in the form of we had a unified matrix representation for that, which we had said V star, the vector, the column vector V star was the matrix A, or rather the geometric transformation matrix A product with the column vector V, and the column vector V indicated the original coordinates, right. So we had defined that how this how the structure of this A matrix will be. Basically these column vectors B star as well as V, we had made it into a 4 by 1 column vector. So 4 by 1 means the 3 elements, the top 3 elements were indicating the x, y and z coordinates. For the case of V, column vector V, it was the original x, y, z coordinate, and for V star it was the transformed coordinates x, y, z, and the fourth element was equal to 1, and this A was defined as a 4 by 4 matrix. So with this kind of a unified matrix representation, we will express the perspective transformations. But before we do that, let us consider the imaging geometry. Now, I have considered a 3-dimensional Cartesian coordinate system. The capital X, capital Y and capital Z. This is the Cartesian coordinate system which I have got for the 3-dimensional world. And any point in this 3-dimensional space will be having a coordinate which is referenced to these 3 axes. Okay. Let us consider some point P which is having coordinate capital X, capital Y and capital Z. Now, we are going to consider its image point on a camera. So, let us now have a camera, okay, and for that camera we consider that, for simplicity, let us assume that the camera's photographic plate is located on an xy plane whose z coordinate is 0. So, we are going to consider this particular plane. This is our photographic plane of the camera, and we assume that the camera has got a focal point over here. Supposing this is the focal point of the camera, so that where we are going to find the image of this point P, if we join the point P with the focal point of the camera and then extend that line, okay, the point where that line intersects with the imaging plane will give us the position of that particular point as seen on the image. Is it right? We have the photographic plate located over here, and this point O is the focal point of this camera, and in order to get the image of point P on the photographic plate, what we need to do is to join P and O, and let us say that at this particular point we have got the image of this. Now, how to represent the image coordinate? Let us say that the coordinate system for the camera is written as small x, small x, small y and small z. Supposing this is the coordinate for the camera. small x, small y, small z is the coordinate system for the camera, and capital X, capital Y, capital Z are for the world coordinates. Now, the point P is now seen over here, and which coordinates should we consider? Let us say that this is the image point, say Pi is the image point. What will be its coordinate? Let us say small x, small y and 0, because we are considering the plane z equal to 0. The plane small z is equal to 0 we are considering for the camera's photographic plate. Of course, in this case we have aligned the capital XYZ coordinates with the small xyz coordinates. For our simplicity, we have assumed the same coordinate system for the camera as well as the world coordinate. But it is not mandatory that we have to use the same coordinate system. We can have a different coordinate system also, or rather this assumption we can violate. But let us first have this simplification assumption that we have the same coordinate system. So, I will represent the coordinate of this point Pi by simply xy, because I have for the entire photographic plate I have the z component equal to 0. Okay. Now, in order to find a relationship between this capital XYZ and small xyz, we need to know some other parameters of this imaging. Now, one such parameter which we must consider is the focal length of this camera, and let us say that the focal length for this camera is equal to lambda. Say lambda is equal to focal length for the camera. Okay. Now, we will find that if we draw if we look at this triangle and if we look at the triangle which will be formed by considering this point O, the point P and the perpendicular drawn from P up to this z axis, then this triangle and this triangle will be similar triangles. Okay. And considering the similar triangles, let us say that this point is the point Q. What is the distance OQ? Supposing this is O1, O1 is the center of the coordinate system over here, and O is the focal point. So, I already know that O1 O distance is equal to lambda. And what is the distance OQ? OQ is going to be capital X or rather capital Z minus lambda, because the distance O1Q is equal to capital Z and the distance O1O is lambda. So, what we have for OQ is Z minus lambda. Okay. Now, considering this similar triangle, now this distance PQ will indicate to you capital X, because this is along the X axis. Look, I am considering a point in the 3D space, right? And really speaking, this distance PQ which I have drawn, okay, that is parallel to the X axis. So, indicate the distance PQ will indicate the X. Yes. So, I have considered that point, okay, on the XZ plane. I have considered the point P on the XZ plane. Then the distance PQ will give me X, and I will have a relationship like this from the similar triangle. What I will have is x by lambda, that is to say this will be having a coordinate x, okay, and this divided by lambda, that is for the smaller triangle, x divided by lambda, that will be equal to minus capital X by z minus lambda, which we can write as x by lambda minus z. And very similarly for the y coordinate, we will be having y by lambda equal to minus y by z minus lambda, which will be equal to y by capital Y by lambda minus capital Z. From the similar triangles, this is what I will get. Any doubts? Now, can you tell me that why I am having a minus sign over here? Yes, somebody has answered correctly that we are having a minus sign because the image point and the object point, they are situated on the opposite sides of the camera's focal point, or rather camera's focal axis, okay. Rather there is an inversion in the image, and that is why we have a minus sign over here, minus sign for both x as well as y, and we can have this x by lambda expressed like this. And we were really interested in knowing small x and small y in terms of the world coordinates capital X, capital Y, capital Z, and the focal length lambda. So we have x equal to lambda capital X divided by lambda minus Z, and we have y equal to lambda capital Y divided by lambda minus Z. This is small xy written in terms of capital X and capital Y, capital Z, and lambda. Is that clear? Very simple. From similar triangles, this is what we are getting. But actually speaking, what we should try to do is to have this world coordinate as well as this image coordinates, we should represent in terms of that 4 by 1 column vector which we were doing the last time, okay, so that we can also define the elements of the 4 by 4 transformation matrix, okay. So from this Cartesian coordinate system, which is having only 3 components x, y, z, we will now go over to a homogeneous coordinate system having, instead of 3, we will have 4 elements there in the homogeneous coordinate system. Now the world coordinates, okay, the world coordinate vector can be defined as w equal to, the vector w will be x, y, z, okay. 3 elements, just these 3 elements x, y, z, indicating the x coordinate, y coordinate, and z coordinate. This is the world coordinate w, and from this we will have a homogeneous coordinate defined. We are now defining another vector, okay, wh, which will be not a 3 element vector but a 4 element vector, and we can define the 4 element vector like this. We can say the first element is kx, the second element ky, the third element kz, and the fourth element k. The idea is that if we divide the first 3 elements of this vector by the fourth element, which is equal to k, okay, if we divide the first 3 elements by k, in that case the first 3 elements will give us the Cartesian world coordinates, okay. We will get the elements of this w from here. So this is how I am defining my wh vector consisting of kx, ky, kz, and k. And what my objective is to get a homogeneous camera coordinates which I will call as CH. The vector CH will give me the camera coordinates in homogeneous notation. So this is homogeneous world coordinates, and this is homogeneous, CH is homogeneous camera coordinates. Both CH and WH will be represented in the form of 4 by 1 column vector, 4 element column vector. So my objective will be to determine the elements of this column vector, and to get this column vector, what I should do is, this CH I should get as a product of this a product of the transformation matrix P, which should be a 4 by 4. So there should be a 4 by 4 matrix, okay, which will denote this perspective transformation. Perspective transformation means from the world coordinate point at P, I am getting the image point Pi. Image point Pi will be the transformed point. The world point P will be the original point. Now, this is the matrix P, which will indicate that perspective transformation, and this should be a 4 by 4 matrix. The idea is such that if I multiply this 4 by 4 matrix with the world coordinate as we had expressed in the homogeneous form, okay, consisting of this kx, ky, kz and k, okay, if I multiply P with WH, I should get a column vector which will give me the homogeneous camera coordinates. Now, what should be this P? Let us investigate. Supposing we take the transformation matrix P something like this: 1 0 0 0 0 1 0 0 0 0 1 0. So far I am about to construct a identity matrix, but the difference is in the fourth row. In the fourth row I am having the last diagonal element also as 1, okay, and this element, if I had made 0, it would have resulted in a identity matrix, but instead of that I am having an element which is 1 upon lambda, okay. If I define my transformation matrix P in this form, the WH vector is already given to me as kx, ky, kz and k, okay. Can you tell me that what will be the composition of the 4 by 1 vector CH from this relation? Not k by lambda. I think somebody has given the answer, but the last element was not correct. So obviously, taking the product of this P with this WH, we should get CH as KX is the first element, KY is the second element, KZ is the third element, and what is the fourth element? Sorry, I made a mistake, so please do this correction. This is not 1 upon lambda, this is minus 1 upon lambda. For the P vector, for the P matrix, this element is minus 1 upon lambda. Please make this correction. So, if we do that, then what we are getting is minus kz by lambda plus k. So, this is the camera coordinates in the homogeneous form. Rather, the transformed points we are getting like this. Now, in order to get the C vector is a 3 element vector which will indicate to us the transformed point, okay, after undergoing the perspective transformation. That is the transformed world point after undergoing the perspective transformation. Now, how to go from the homogeneous coordinate back to the Cartesian coordinate? We have to divide the first three elements by the fourth element. Okay, do that. Just see what do you get. The first element to be divided by the fourth element should give me the first component of the Cartesian coordinate. Second element divided by the fourth element will give me the second element of this. Third element divided by the fourth element will give me the third and the last element for this C vector. C vector will be a 3 element vector. Has anybody come up with the result?
Lambda x divided by lambda minus z, lambda y.
Okay, I have got the correct answers from you. This C vector, okay, which we will talk as small x, small y and small z, because small x and small y I am assuming to be the coordinate of the transform point, and for completion I am also indicating this z. Of course, in this case, in our case, z is equal to 0. But now these three elements will be, by dividing this with the fourth element, what we get is the first element is lambda x divided by lambda minus z. The second element is lambda y divided by lambda minus z. The third element is lambda z divided by lambda minus z. So these are the three elements for this C vector. Now obviously this means to say that x is equal to lambda x by lambda minus z, y is equal to lambda y by lambda minus z. These two relations we have already got. In fact, if you just go back to the earlier thing, you will find that we already got x and y in terms of capital X, capital Y, capital Z and lambda like this. So we are getting the exactly same relation. That means to say that whatever transformation matrix P was defined, okay, is really transforming our 3D world coordinate point into a proper image point. Okay, we have got that from the, by application of similar triangles from the imaging geometry we got that, and now by applying this perspective transformation mathematically we are getting the same point. Of course, we are not interested in z here because z we already know is equal to 0. So we can ignore the third element of it because it is projection on the plane z is equal to 0. That is exactly what we are considering. So the third element can be ignored. Now since this is the transformation matrix, okay, I mean, what type of transformation? It was our CH vector was the product of P matrix and WH vector over here, isn't it? So that means to say somebody had given us the coordinate of the world point and we had got the camera point by applying the perspective transformation. If we try to do the reverse, what should we do? The inverse operation. That means to say that if somebody gives me the camera point, okay, CH, in order to get the world point WH, okay, what I should do? I should multiply it with the P inverse matrix, okay, and if the matrix P is defined in this form, okay, you can verify this very easily. My P inverse matrix for this P, if this is my P matrix, my P inverse matrix will be 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 1 upon lambda 1. So this is the P inverse matrix, and now I have to multiply this P inverse matrix with CH. CH is given to us. Let us say that we have got a point, okay, on the camera which is x0, y0 and 0. So the camera point is, or rather the image point is, so the image point in camera coordinates, or rather this is C. So I should define a CH as follows. I should define my CH as kx0, ky0, 0, k. Agreed? This is what my given CH vector is. Given CH vector elements are kx0, ky0, 0 and k. The inverse of this perspective transformation matrix is given over here, and the problem is now to determine this world coordinates. In terms of this WH, we should get the world coordinate point. So that is the problem which we will discuss in the next class, but may I request you to solve this problem beforehand, because we are going to see some interesting result and observation out of it. So please do it as an exercise. Do this P inverse CH multiplication and see what results for that WH. Okay, and from the result which you get, okay, we are going to find some interesting observation in the next class. Okay, any questions? Okay, thank you.